So in our last lesson, we essentially learned a new operation. We learned about the scalar product. And this entire chapter has basically been about algebra on a whole new type of mathematical object. We've been learning how to do old things we used to know how to do, but now with vectors. And now that we have a new operation, we hopefully are curious about what sorts of properties it has. So we're going to be sort of dealing with questions like, is the scalar product commutative using addition and multiplication? Um, is the scalar product associative, like addition and multiplication? What sorts of things can we prove using the algebra that we have on the scalar product? So by the end of this lesson, will know several properties of the scalar product and how to use them to prove statements and show relationships between vectors. Before we get into that, let's go and take a deep breath. And let's keep learning about vectors. So in mathematics, when we're working with a new operation, it can be helpful to look at how similar it is to other operations that we already know about. And it's going to be really helpful for you to know that the scalar product, the thing that we learned about in 13D, the scalar product shares a lot of properties with multiplication of the real numbers, but it doesn't share all of those properties. So things that it shares, the scalar product is commutative. Okay, what it means for it to be commutative is that it doesn't matter what order you perform the scalar product in. If you do A dot B, it's the same as doing B dot A. So that means that the scalar product is commutative. Okay. Another property that the scalar product has that's similar to sort of normal multiplication is that the scalar product is associative with scalar multiplication, which means that if I have, a vector A that's been multiplied by a scalar K, and then I do the dot product of that with B, that's the same thing as if I do the dot product first and then multiply it by this scalar, this real number K. And then the third property rather, that's shared by the scalar product and multiplication of the real numbers is that the scalar product is distributive across vector addition. And really, that just means that we can distribute a dot product across addition. So if someone wants you to do the dot product of A with the sum of B plus C, you could distribute the A into this and do A dot B and then add A dot C. So really briefly, we're just mentioning here that the scalar product, sorry, no, the vector product is actually something different. The scalar product is commutative, it's associative, and it's distributive across vector addition. Now, the next thing that I was going to do in this video is I was going to have us sort of prove one of these statements. But before we do that, it might actually be helpful to sort of see this in action with something, right? So let's say that you wanted to show someone that associativity like worked, right? So suppose that and this doesn't prove it, but it might show it for an example. So if I have a scalar like 3, so 3 times the vector 1, 2, 3, right? And then I wanted to do the dot product of that with the vector 1, negative 1, 4, right? If I did this in this order, my first sort of scaling of this would give me 3, 6, 9. And then when I do the dot product of that with 1, negative 1, 4, we know we're just supposed to multiply these across and add, right? So this would be 3 minus 6 plus 36. And when I put those things together, I'm going to get 33. Now, if this is associative, I should get the same answer when I do it this way instead. So I should get the same thing when I do 3 times the dot product of 1, 2, 3 and 1, negative 1, 4. And so we can check that, right? I could do the dot product first. Oops, I suppose I don't need all of that, right? If I was going to do the dot product of these things, I would just be doing 1 times 1 is 1, minus 2 plus 12, and then that would all get multiplied by the 3. We're just holding on to that real number multiplication for the end. This is going to get me 3 times 11, which sure enough is 33. So you notice that it didn't matter whether I did it this way or this way, I got the same answer. Again, this doesn't prove that it's associative, but it shows for one specific case that it worked. But throughout this class, in theory, we've been learning that to prove things, we need to do more than just show that it works for one case, or show that it works for 2, or show that it works for 100 cases. We need to show that it's always going to work. So in this next example, I'm asking us to prove that the scalar product is distributive over vector addition. And maybe I would say that, like, let's say that we're going to do this with three-dimensional vectors. So in other words, I'm asking us to show or to prove that when I do A dot B plus C, I'm going to get the same thing as when I do this. Okay? So to prove this, I can't use specific numbers. I need to use something general, right? So I would start this proof off by using a let statement. I would do something like saying, let A be the vector A1, A2, A3. And then we would let the vector B be B1, B2, B3, and I'd let the vector C be C1, C2, and C3. Okay, so I've sort of made these general vectors. These numbers could be anything, right? And I've got all of this stuff here. Okay, so then the next thing we would do is we would basically separate this into, well, let's simplify the left-hand side, and let's simplify the right-hand side, and let's show that those two things are the same as one another, right? So if I was going to do the left-hand side first, I would be leaving A1, A2, A3 out here, and then doing the dot product of that with the B vector plus the C vector. And so when I add those together, I'd wind up with like B1 plus C1, and then B2 plus C2, and B3 plus C3, right? So then I've got this. To do the dot product, I would just multiply these things straight across, right? And this is, again, not going to be pretty, but we can do this. So this would be A1 times B1 plus C1 plus A2 times B2 plus C2, and then plus A3 times B3 plus C3. Okay, so now we've kind of got a sense of what the left-hand side is. Now, on the right-hand side, I'm going to go through and I'm going to do this the other way, right? So I'm going to go through here and I'm going to work this out using these letters that I've defined. So I'd say pause the video and sort of work that out and see if you can show that this is the same as this blue thing that we got from the left-hand side. All right, so if I was going to do A dot B, I would, I'd be doing essentially A1 B1, A1 times B1, plus A2 B2, that's me multiplying these together, and then plus A3 C3, that's these ones. So this is all the first dot product. And then I would do plus, okay, so now I need to do plus the A vector dotted with the C vector. So now this one would be A1 C1 plus A2 C2 plus A3 C3. And then my question becomes, is that the same as this thing here, right? And we could either work with this thing and we could factor it, or I could go over to this one and potentially just sort of like expand all of these things out, right? And I'm running out of space a little bit here to sort of show all of this. But let's see here. I'm thinking that maybe I just kind of do this via factoring, right? If I grabbed this one and this one, couldn't I factor an A1 out of that and I'd be left with B1 plus C1? Well, that matches this piece. And then if I grabbed, let's see here, this one and this one, I could factor out A2 and I'd be left with B2 plus C2. Well, sure enough, now this matches this part. And then the last part here, I might have to use green for this. If I grabbed these two, I could factor out the A3 and there would be a, oh, whoops, I just realized I had a typo up here. This should have been a B, huh? B3 plus C3. Okay. And at this point, like I've got these things, right? And so just like we've done with proofs before, I want to write something. I want to write something like we've shown that the left-hand side is equal to the right-hand side, and therefore we have proven the thing that we wanted to show. So remember, we like to start our proofs with some sort of a let statement. We need to sort of define things. We often, in direct proof, we work with the left-hand side, we work with the right-hand side, and then we like to sort of conclude our work by writing a sentence or two, sort of putting something together that summarizes what it was that we did. All right, so now let's look at a couple more properties. Okay, so let's recall from our last lesson from 13D that the dot product is supposed to be equal to the product of the magnitudes of the vectors and the cosine of the angle between those two vectors when they're placed with their tails sort of touching one another. So this relationship leads us to two other properties of the scalar product. So the first one is if two vectors A and B are perpendicular, then the angle between them is 90 degrees, and we know that the cosine of 90 degrees is 0. And so that means that whatever these magnitudes are, if the angle between them is 0, the cosine is going to be 0, which means that whole dot product is going to be 0. So if two vectors are perpendicular, their dot product is automatically 0. Just realized I was missing a little vector line over the top of that one. The second property is what happens if A and B are parallel? Okay. If A and B are parallel, it means that you've got one vector here and another vector here. They're going the same direction, right? It means that when I do the dot product of those two vectors with one another, right, because the angle between these things is going to be 0, the cosine of 0 is 1. The dot product of these two things will just be the product of the magnitudes of those two vectors. Okay. Now, as a follow-up to this, it's worth noting that because A is parallel to itself, because a vector is always going in the same direction as itself, this also means that the dot product of A with itself is equal to the magnitude of A times the magnitude of A, which is the magnitude of A squared. And this ends up being a really, really neat property that we can use to our advantage when we're working through some kind of weird show problems. So it's kind of worth noting that if you're ever working on a show problem and they tell you something about the magnitude of a vector squared, you can transform that into a dot product. So you can go this way, but you can also go the other way around. So these are neat properties that we're going to use as we get into some more sort of interesting and weird problems. So let's look at one of those now. All right. Now, I know that for a lot of you working with this new thing, these vectors might be challenging. It might be weird. It might be kind of scary. You don't want to make mistakes. But we learn through making mistakes. I would really encourage you to pause the video and try working through this. Even like you take a shot at like a first step here and see what you can do. So the example says, given that A and B are perpendicular vectors, so we're given some information about that, there's something we can use that for, such that the magnitude of A is 5 and the magnitude of B is 3, use the properties of the scalar product to evaluate this thing. One little bit of a hint that I would mention to you is please remember that this thing right here is the magnitude of A, right? This over here is A itself, right? So you can't just take 5 and plug it in here. Like this has to be the vector A. So think about what you could do with the properties of the scalar product for this, and hopefully you'll be able to think of or see ways that you can bring the perpendicularity of A and B in and these magnitudes in. All right, so hopefully you've given that a shot on your own. The first thing I'm thinking is we know that the dot product is distributive, right? I can distribute the dot product across addition. But if I can distribute the dot product across addition, it basically means that I can also sort of foil a dot product. I could distribute this thing to A and to this, and then once I distributed them, I could distribute the A to this one and to this one, and the B to that one and to that one, right? So at the end of the day, what this means is that I can do 2A dot A, right? And then plus 8A dot B, and then minus B dot A, and then minus B dot 4B. Okay. So I basically used the distributive property of the dot product to sort of foil, as it were, this thing out. Okay. So now we have to start thinking, okay, how can I use the perpendicularity of A and B and these magnitudes to evaluate this thing? Okay. Well, what do we know that A dot A is? We learned previously that A dot A, because A is parallel to itself, this is just going to be the magnitude of A squared, right? And what about A dot B? Actually, what about A dot B, right? A and B are perpendicular to one another. So what is the dot product of A and B going to be? It has to be 0, right? So this is going to be plus 8 times 0 minus, what about the dot product of B and A? Well, it's commutative. It doesn't matter what order I do it in, it's still going to be 0. Another way to think about that is if A and B are perpendicular, then B and A are perpendicular. So this is also 0. And then over here at the end, I've kind of got a weird thing here. Remember we said that the dot product was associative? It means that this 4 can kind of just be brought out here, right? I can say minus 4 times B dot B, but we know that B dot B is the magnitude of B squared. Okay, so do you see how I'm using these properties to sort of work through this thing? So now I have 2 magnitude of A squared minus 4 magnitude of B squared. Well, but we know what those magnitudes are, right? This is 2 times 5 squared minus 4 times 3 squared. This is 2 times 25, so that's 50. 50 minus 4 times 9 is 36. So I'm getting this to be 14. So I was able to figure out what this thing was, even though I didn't know either of the vectors exactly. I just knew that they were perpendicular, and that's what their lengths were. And so this is what that dot product is. Okay, so this video really just has 2 more examples that we're going to go through of sort of using some of these properties and working with our knowledge of the dot product. Okay, so this next one says, consider 2 non-zero vectors A and B. So non-zero vectors means they're not equal to 0, such that the magnitude of A plus 2B is equal to the magnitude of A minus 2B. And they want to ask you to find the value of A dot B. Again, I'd encourage you to try and work through this on your own and see what you can do. If you want a hint, I'll give you one right here. My encouragement to you would be to think, if this is true, then I could square both sides. And if I squared both sides, then I would have a magnitude squared. And remember that a magnitude squared is equal to something with a dot product. Notably, the left side is going to be A plus 2B dot A plus 2B. I can turn a magnitude squared into a dot product of that vector with itself. Okay? So if we know that about the left-hand side, we could probably do something similar with the right-hand side. And then maybe I can work with that equation that we have to figure out what A dot B is. So that was my long-winded hint. So if you haven't paused the video, if you haven't tried this on your own yet, see what more you can do by working with the right-hand side and see what you get. So the right-hand side, we know that we could also do A minus 2B dot A minus 2B. Okay. And then sort of from the previous problem, we now know or recognize that I can basically FOIL with a dot product. And so when I FOIL this with a dot product, I'm going to end up with A dot A and then plus 2A dot B. I did this one with this one and this one with this one. Then here I'm going to get plus 2B dot A and then plus 4B dot B. And this is going to be equal to, now, frustrating, I'm running out of space here, so I'll have to write this down on the next line. So when I distribute this one, I'll first send the A to both of these. This is going to get me A dot A, and then minus 2A dot B. And then here I'll have minus 2B dot A, and here I'll have plus 4B dot B. This is a really long equation, but hopefully we notice that there's going to be a lot of stuff here that we can work with, right? It looks like both the left side and the right side have an A dot A. So I could subtract A dot A from both sides, and that would drop out. It looks like the left and the right side both have a 4B dot B, and they're both positive, so I could subtract that from both sides, and those would drop out. And then the next thing we notice is, wait a minute, this has an A dot B and a B dot A. Those are the same as one another. So I could basically combine these to get 4A dot B. So 4A dot B is equal to, hey, wait a minute, same thing's going to happen here. This is A dot B, this is B dot A, this is negative 4A dot B. And this is great. This problem wanted me to find the value of a dot b. Like, there it is. I just need to find out what its value is. So, but wait a minute, those two things are the same as one another. That means I can add this to the other side. I'll have 8 a dot b is equal to 0. And so the next thing I can do is just divide that 8 over to the other side. So when I divide that 8 over, I'm going to end up getting that a dot b is 0. And that was what the question was asking for. Interestingly enough, and I don't want to dwell on this for too long, but there's an interesting thing that this problem actually gets at, right? What it gets at is if you have a vector A and a vector B, right? And if somebody told you that A plus 2B was the same as A minus 2B, if they told you that this was the same as this, the only way that can happen is if the A and B vectors are perpendicular to one another. So like this one, see how this is shorter than this one is? The only way this would work out is if I had A and then B that was perpendicular to that, because then it wouldn't matter which way I went, I'd wind up with like a congruent triangle on either side. The problem wasn't asking for that, but it's neat to see that for as much as we made a really strongly like algebraic and proof-based argument, this has a geometric consequence. So hopefully that made sense. I've got one more example for us to look through in this lesson. So the last few examples that we've gone through here have been basically about showing and about proof. And this next one is going to be a lot more about sort of like using these to do kind of an interesting thing. And the skill that we're learning here is really going to turn into other things, like as you get further into vectors, and we're really kind of just like playing with some of this here. So let's see here. We know that there are these points A, B, and C. So points A, B, and C have position vectors of these vectors. Part A is to find vector BC. Now this should be reviewed. This should be straightforward, right? How am I going to find BC? BC I'm going to get by doing OC minus OB. Right? And we were given those things, right? I just need to do this one minus this one. So if I subtract these two things, 1 minus 3, 1 minus 4, and 5 minus negative 2, this looks like it's going to be negative 2, negative 3, 7. Okay, so that's BC. I did part A, yay. Part B. Part B says find an expression for AB in terms of K. Now remember, we know what this vocabulary means. When somebody says find something in terms of K, it means it's okay if K is around in the problem, right? I just want an expression for AB, right? So for part B, when I want to do AB, what two vectors do I need to subtract? I need to do OB minus OA. And if you haven't already done so, I'd encourage you to pause the video here and think about how you would subtract these. How would you write an expression for AB? I mean, and your answer should look like a vector. So how would you write an expression for this? Well, hopefully you recognize, wait a minute, I could just do the first coordinate of B minus the first coordinate of A, which is going to include K. So this is going to be 3 minus 3K. Then for the next one, I would do 4 minus a negative K, so 4 plus K. And then for this next one, I would do negative 2 minus 1K. So negative 2 minus K. And there it is. There's my expression for AB. Now part C, we're going to take these two things and we're going to put them together. Okay? Part C of this problem says, okay, find the values of K for which AB is perpendicular to BC. Find the values of K. So that means my answer here is going to be a value of K, like K is 2 or K is 5 or K is 17. Find the values of K for which AB is perpendicular to BC. So what am I going to do here? How am I going to ensure, part C, how am I going to ensure that these two vectors are perpendicular to one another? What do we know about perpendicular vectors? Hopefully we know that their dot product is 0, right? So this problem is really just asking me to do BC dot AB and set it equal to 0. If you haven't already tried this on your own, pause the video, give this a shot. Okay? So let's see here. BC is the vector negative 2, negative 3, 7. The vector AB is this expression that we came up with. So this needs to be equal to 0. And then for a dot product, I know all I need to do is multiply together the components and add them together. So this will be -2 times this, that's -6 plus 6k. It'll be -3 times this, that's -12 minus 3k. And then it'll be this times this, that's -14 minus 7k. So now I can combine like terms here. 6k minus 3k is 3k, 3k minus 7k, this is -4k. And then I've got -6, -12, that's -18, that's 18, 28, 32. So -32 equals 0. And then, I mean, this is just a little two-step equation, right? If I move the 32 over, -4k is 32, which means k has to be -8. So that is the value of k that will force these two things to be perpendicular to one another. It turns out that that skill, that ability to do things is going to end up being really valuable when we work with vectors representing lines and finding relationships between them. So this is very much a skill that we're building so that we can work and use it as we get deeper into our knowledge of vector geometry. So, as always, I hope that made sense, and I hope that if you had questions, you made notes of them as you were taking your notes, or that you'll ask me about them. I really enjoy vectors, and I love getting a chance to talk to people about them. So best of luck in the assignment, and I'll see you in the next video.